the number e. So if you've taken some sort of algebra 2 or pre-cal in high school, this might seem familiar. E is just another constant that people typically write out as about 2.73. And something you should realize is that it's actually just an irrational number. It's actually very much compared to pi. But the big idea here is that it has to deal with this equation. So if you want to know one little fun fact about the exponential function that I guess kind of gives you intuition as to why it's called this, is that e helps us calculate exponential growth / decay. So that's like the big idea. There's only really this one statement. And what I mean by exponential growth and decay, well, you've already seen it in the last class. It's essentially graphs that look like this, or even in the Popper index. So e to the x will look very much the same. However, whenever we deal with e to the x, we only really care about the base point. Everything else is just very standard. We don't really keep extra points because the other points are going to be at a decimal, and you don't worry about it. So, all I'm saying from here is that e is a very special constant. If you want to know why you get e, it to be exactly this decimal, then take it to cal. Oh, sorry, not to cal, to cal. Okay, I'm going to skip this slide. The idea here is just getting historical context. It doesn't matter for your exam, but you can read it on your own. So, some important details about the exponential function. So, some important details have to deal with the domain and the range, as always. So, this is actually going to be the exact same stuff that you would deal with from the other exponential functions that we looked at. So, the domain is always going to be -infinity to infinity, unless you break it somehow, which you won't do that in this exam. Your range will be 0 to infinity if you're just looking at e to the x. And that makes sense because you're only looking at everything above 0. The key point is that 0, 1, again, that's the only one you really want to care about. And then the horizontal asymptote is at y equals 0. And again, the idea here is you want to remember that you're approaching that value. So the idea here is that we're going from 0 to 0. Is that as I go to -infinity, you're approaching.
So, the Windows section will be in, so we can comfortably on Monday.
This is just a really good slide to kind of reference a lot of the multiple choice in the quizzes, in the homework for this week, and on the exam, we'll rely on this slide. So it's just little bullet points. But a lot of this is basically identical to what we did last week. Okay, so you can imagine exactly what we're about to do. So basically, we just gave you another parent function, and now it's just more drawing, more transformations that hopefully everyone's comfortable with by now. So, we're going to just go ahead and do a couple of these, and then we'll go to 5.3, which will be logs, which will actually have a tiny little bit of algebra, but that's so, sketch the graph of this new function. Well, your parent function is e to the x, which we already have a graph of from the previous slide. We only care about one point. So you go ahead and just really draw this one, and then the rest is this one. Then we can apply all of our transformations. So let's switch to the blue. First, I want to notice that we have a vertical reflection. So I want to reflect it across the x-axis. So I'm just drawing these arrows for reflection. Okay, and now we have some other transformations that I can do in green. We have this +2 on the inside and the outside. and these are going to be horizontal and vertical shifts. In particular, you're going to have to the left and to up. So we're going to bring everything in blue down, center down. We're going to bring it up. And then you point here. The big thing you have to remember is that the horizontal asymptote also has to move up. So this horizontal asymptote has to go up by 2. So these are always the horizontal asymptotes. And then I can go ahead and draw the graph. A little bit rough, but it won't matter. We just need some sort of approximation. So green is the final answer. Any questions? Any questions? And I know that I tried to use the color to kind of help out a bit, but it's a little bit awkward to see. But again, it's the same things over and over. Pretty much everything in this class kind of stacks, which is nice because then if you fall a little bit behind, you can catch up. Okay. Oh, I should write I forgot to write all the stuff. So, sorry. Domain will always be negative infinity to infinity. The range in this case will be negative infinity up to 2. Now, why is this the case? I can go ahead and highlight it. That's because we start at this horizontal asymptote, and our graph is going down. Right? I can highlight it. And then the horizontal asymptote, we already wrote it down, but I'll just write it down again one more time. Is white. The key point is that unity point. So, nothing crazy, same thing that we did last week. Now, if this one's okay, then everything will follow pretty nice. Cool. So, we're going to do more of this. So here we're going to go ahead and deal with the graph of 0 minus x. So we're going to have a little horizontal portion there. So, we're going to do the same exact thing. We start off with the parent function, which is y equals u to the x. Okay? Let me go ahead and roughly draw this thing. Cool. And now we can go ahead and start applying our transformations. Now there's a few different ways you can do this. I'm going to again do it in the order that I like to do it because I think that it makes a little bit more sense to do it that way. I always do reflections first. So first you should notice you have a horizontal reflection. So you're going to flip it horizontally. You're going to flip it like that. Alright, there's nothing down there, so I'm not going to do that. And this will look like this. How do I? There you go. Okay, cool. And now we can do our translations. So our translations will be, we're just going to have one horizontal and one vertical. So we're going to be one to the right and one down. And that comes from this and this. So we're going to move the key point over by 1 to the right and down by 1. And the key thing here that you have to remember is that the horizontal asymptote is always going to be this last number on the outside. So your new graph will look like this. Oh my god. There's a lot of asymptotes. I'll highlight it just to make it easy. When you write down domain and range, hopefully this timeline can help out a little bit. The domain is never going to change unless you do any sort of crazy bits, which you won't do. Domain will be negative infinity to infinity. Just kind of force you to come with that. The range, you can just look at it from the graph. You start at -1, and then you go up to infinity. Here's the highlighter. The asymptote is y equals -1, and if you point is one comes here.
4. Yeah. 35. 25. Yeah. Got 80 on the first one though. I'm doing bad in this class. Just
Here's speed limit of the wall.
Average.
What?
Okay. That's pretty good.
Yeah.
Be over. So then the next one. Fair. Yeah. I still like algebra.
Oh, because it's going down below the graph.
I can do better statistics.
So you start at the horizontal asymptote.
Well, SAS is easy. I'm worried about calc. I don't have to take calc, so yeah.
Cool. So, now we just have to go ahead and write down some equations. So we're just going to go ahead and this is basically just like one of the multiple choice type questions where you and you go ahead and write down the equation. Alright? So here they say they ask you to write down the equation of a natural exponential function. So in other words, y equals udx. But in particular, you're going to shift it. You're going to shift it by 3 units to the left. So in other words, you're going to write y equals e to the x plus 3. And then you're going to shift it by 3 units. Or not 3 units, 1 unit down. So it's going to be y equals e to the x plus 3. And then finally, you're going to have a reflection on the x-axis. So you're going to have a reflection on the x-axis. Now, I want to emphasize what this, like the way you should remember this, because it's reviewed this, it's good to have a picture. The x-axis is this horizontal axis. So in other words, this is a vertical reflection.
Have they told you where they're going to put you yet?
So you need to put the
Probably just in
negative
the second game.
in front of the e. No. On the multiple choice that I'm looking at, there's obviously like the same exact answer, but like in different negatives or different places.
But
The
now
plus
I'm not
three
sure.
using the outside for one of them.
7.
But this is how I recommend you do this. You shouldn't really try to memorize the whole reflected on the x-axis thing. Even I
First
would
aid or
try
forwards?
What
do you do? I'm the light forward. Basically, my job's going to be somewhat quick.
Okay, so standard types of questions that can obviously be expanded into multiple choice formats. So determine the domain of the function. This is an exponential function. So that means that the domain is always going to be negative infinity to positive. If they ask you for the range of the function, then you have to go ahead and kind of either draw this, or you can just try to think about it conceptually. I'm going to go ahead and quickly draw it as an outline, that way it looks a little bit nice. So, I'm going to roughly draw this. This is y equals e to the x. And then from here, I'm going to apply the vertical reflection. So it's going to look like this. And then from there, there are these transformations here. These are the translations. To right.
The sky. Already
Yeah.
super heavy. Yeah, it's pretty heavy package.
So then we're gonna
This will be the
have,
third time I've gone to it.
the following.
I love them. I think the first one I went to was terrible. Not terrible, but still cool. But it was like blow up.
And then we're gonna go over.
No, it's just and you couldn't really see anything. It was really sad. This time, it won't be in the morning, so there's not as much risk of that.
Okay. So I decided to draw this because it felt a lot easier to just draw it than
last
to
time. Last time we never lost sight of the booster.
From here, what's going to happen is you can just kind of look at the graph and get the range out of it. So it starts at 3, and it goes down to negative infinity. So the range is going to be negative infinity all the way up to 3, because you have to measure it from the bottom up. Now, to determine the y-intercept of the function, you plug in 0. And this is the part that's always a little bit weird, because it's gonna give you some not so nice numbers. Right off the one. F of 0 will be negative e to the 0 minus 2 plus 3. This is going to be negative e to the minus 2 plus 3. And this is going to be equal f of 7.
So cool.
Okay, good. The version I have is this. Determine the asymptote of the function. Y equals 3. Very easy. All you have to do is look at the last term. And you can even look at it here from the here. And what transformations occurred? Well, you had a vertical reflection. A vertical reflection. You had horizontal shift. And a vertical. Basically the exact same question that we did prior, but we just went ahead and had like an open ended. Yeah. Yeah. Right. Isn't that what we just did? Okay, yeah, good. The pictures up here. Okay. And then finally, this question. This one's tricky. This one's actually really tricky because it has a bit of lies and deceit that have been hidden. So I'm going to zoom in a bit because these numbers are hard to see, and I'm going to outline them also because otherwise we might not be able to completely read them. Okay. We're asking which of the following functions is displayed here? So I want to go ahead and tell you how you should do this using essentially a process of elimination. So the idea here is you can basically just decompose this function based on a few properties of the graph. The first thing you should notice is that the horizontal asymptote is at y equals positive 4. So immediately you can knock out f and b because they're at minus 4. There's a minus 4 there. So that would imply that the y-intercept is at negative. The next thing you want to look at is kind of like what the parent function should look like based on the reflections that are being applied here. So what you want to remember is, in this case, we're looking at the parent function of 2 to the x. And that looks like this. Yeah. So y equals 2 to the x looks like that. But this looks very similar except it's backwards, right? So essentially this must have a horizontal reflection attached to it. So this, I'll write that down,
This game.
and I can do it in a different color.
This
This has a horizontal reflection. So, you should actually have something like this. Y equals 2 to the negative x. With a bunch of other things on it. So, in particular, A doesn't have a horizontal reflection, it actually has a vertical reflection, which is bad. C also has that problem, and so we're down to D and E. Yeah. And finally, we have one last thing we need to check, which is just figure out which of these two are the answers, E or E. And honestly, the easiest way to do this is to just plug in points. Like just plug in a point and see what you get. So in particular, what I would do in this case is I like this coordinate here. This coordinate x and y is quite nice. And what I would do is I would plug these in.
same coordinate.
And check which one's consistent. In particular, for answer number D, or answer D, right, you should get 2 to the minus 2 plus q plus 4. Because this is the x value, right? This is going to give you 2 to the 2 plus 2 plus 4, which is 2 to the 4 plus 16, which is 20. And that's not equal to 5. So this cannot be the answer.
It's like, wait, what?
But for answer choice E,
Have you seen that
you're
slide
going to have 2 to the minus
What? You
negative
watched
2
it
minus 2
down there
plus 4.
before.
This is going to
And the song that
give
goes,
you 2 to the 2 minus 2 plus 4,
where their
2 to the 0 plus 4,
America's
which is 1 plus
allegiance
4.
is ruled by expedience.
That's exactly
Call him a Nazi. He won't even frown. Nazi schmazi says where their von Braun.
Any questions? There's a longer way to do this. There's a longer way to do this that basically requires you to do a system of equations. And I'm not going to recommend you do it.
Here's where they
Because
go
it's
back.
one of the few times
It's
where
not
one
Betty Park that says where their von Braun.
There's no choice. We chose to do this in this case because that way you don't have to do
I remember
just go ahead based on all this.
some will have first words.
Any
Span
questions?
of renown. But something or attitude should be one of gratitude. Like the widow.
Oh, because so the parent function is
Sacred
bad,
books
right?
and all flipped in
It's moving up.
How
So
their
it looks
large
to the right.
pensions do wear their
And
von
so the
Braun.
graph we have is sloping up only to the left. So you can think of it as all as linear to have the horizontal effect. Does that make sense? If it was going down, then you have that vertical. Good question. You know? Yeah, it's always super simple for an exponential function. It's just whatever you're at. Cool. All right. Can I switch?
No, you can't.
I assume people are tired of all these like graph drawings. So you get some quick little algebra breaks. And the good thing is that this section's not too hard. It's more just hard because of the. So
Yes.
logs.
Logs.
Hopefully, some of you see logs at some point.
Yeah, the force.
But basically, I'm only going to do like the very
Drop the
simple
log in the toilet earlier.
So in exam 3, we're only looking at the very basic evaluation of logs as well as its graphs. In the final exam, you might have a couple questions actually related to algebra. So nothing crazy yet. And even then, it's just going to be algebra. Just standard algebra. So, I want to emphasize the connection that's in this line. It's this line is exactly what you have to remember. The way I've always thought of logs is that they're just another way of writing an exponential function. And in fact, it's going to be very important for whenever you want to solve them, because they undo exponential functions. And the big idea here is you want to remember how to use this arrow. The idea is if you want to go from an equation with a log, an equation without, is you just switch whatever is inside that log with whatever the log is equal to, and then you have the exponential form. The idea about the log function is that it is the opposite of an exponential function. So it's still going to be determined by some base, so you're still going to use some sort of base, similar to how you use it in the exponential function. There is a very special log called the natural log. And that's when we use the base e.
What is that?
And there's actually a shorthand for it. We also have the common log, which is the base 10 log. So this is the one we use in like chemistry and physics to kind of denote from decimals. And that one we just kind of assume that the base. So yeah, basically if I ever write log without the base, so if I write log with no base, I assume it's 10. If I write ln, I assume it's e. And obviously all this English makes it seem a lot more complicated than it really is. So let's go ahead and write
It's one class where you can either do 3 tests or 1 final, and so I just haven't done any of the tests.
Okay. So all we're doing for these examples is very rapidly converting the equation. So all I'm going to do is I'm going to write the equation in exponential form. So right now they have logs. I essentially want to write without the logs. We're not going to do any simplification. We're just going to write it without a log. And the idea is always this arrow. Always write this arrow. You can go from the log to exponential.
You're not looking at it until you figure out what's actually going on.
So this is the same as saying x equals. Again, I'm not going to simplify anything. I just wanted to emphasize how you should be writing. So if I want to solve this equation, all I would do is I would write the common arrow, switch everything, and then I can redo. Same thing here. So this means 64 is equal to a squared. And so on, you just go here. You have 3 cubed equals 27. And that's true, right? 3 times 3 times 3 is 27. Yeah. Here, there's no base, so I can go ahead and fill it in a different color. We just assume this is 10. And again, we switch these positions. And you write 10 to the 5th is equal to, what is that? Okay, and for the last one, same deal. Now we're using ln, so I'm going to assume it's base e. And be very careful. Here, this is a little bit large for the typesetting is here. So basically, again, you want to switch all of the things that inside a log. So not the base, the entirety of whatever's inside of the log. So we're going to switch that to the negative 2.
4 days.
So you get that e to the minus 2. Whenever e squared, which is just like a fact, you have a negative exponent.
Better than the bar.
So none of this is going through actual algebra. No simplification. We're not doing anything crazy. I'm only writing these to hopefully give you some examples of what the log actually is. Because if you just kind of memorize logs as like, oh, it's a weird math function, then it's never going to make sense. It's better if you just kind of look at it from the opposite.
Muscular fat, but also just fat.
Okay. Okay, and similarly, we can go in the backwards form. So You want to do this in the same exact way as you compute the log switch. But here remember that you want to turn the base into the log. So the idea here is we're going to do the exact same way, but each of these elements is going to become the base of the log. And then what we're going to be switching is the exponent to the other side of the equal. So you get log base 4 of 64. Similarly, we can keep going. I'll do this for all of these examples. Why not? Log base E, log base 10. If I switch these in, you'll get 64. So log base 2 of 64 is equal to 6. Log base E of 25 is equal to x in this case. And finally, log base 10 of 1000 is equal to x. For these last two examples, you'll actually never see them written like this. Again, you should learn to recognize them as ln of 25 in this case, and log with no base. Okay. Now that I've given sufficiently many examples of how you should read this, I want to go ahead and give one very important statement of how you should really think about logs. So logs solve for exponents. That is essentially exactly what logs are telling you. What the log is doing is it's telling you what exponent you have to take your base to get to the other element. So for example, if I read out, where is it? Let's say it would be green. If I read out this example here, then the log is telling you what exponent of 4, so in other words, 4 to the power of what, will give you 64. That is exactly what the log is solving for. It's solving for exponents. So it's inherently the opposite of the exponential. And we're going to see that at the end of this section. Any questions? Quick thoughts. Okay. More examples, but these are all relatively quick. And the nice thing is, now that we actually feel somewhat of a comfort of what is log trying to solve, you can actually look at evaluating these. So how do I evaluate this? Well, you can write as equals to x, rewrite in exponential form, and solve. This is actually not what a computer does. A computer does a lot of craziness, but this is actually the easiest way to do it by hand. So let's go through each of these. Essentially, you always start off by writing equals x, and then you switch these to rewrite it in exponential form. So I say 6 to the x is equal to 36. And then you have to think to yourself, question, what power of 6 gives me 36? And that's just 2. Because if I do 6 times 6, you get 36. So 6 squared is equal to 36. Implies that's equal. I wrote a lot here, but you never have to write this much. I'm just writing this here, so you have an example of what you should be asking yourself in your head. So really, all you need is to rewrite it. For the second one, same thing. I'll write equals x. And then I can rewrite this as 2 to the x equals to 1/8. This is a bit tricky. This is a bit tricky because this is going to require a lot of rewriting. So you're going to have to do a little bit of extra work. But this is the same thing as 8 to the minus 1, because when you have a minus 1, it's the same as thinking about it as reciprocal. 8 is the same thing as 2 cubed. So then you can combine everything as 2 to the power of negative 3. So in the end, what you have is 2 to the x is equal to 2 to the minus 3. And then at that point, you can just kind of line these up. So I have the same base, and the exponents have to be, in other words, the answer here is negative 3. That one's just trickier because there's a lot of like little bits of arithmetic. For the next one, it's a lot easier. Same thing, you write x, and then you rewrite everything. So 5 dx is equal to 125. Okay, well, 5 times 5 is equal to 25. 5 times 5 times 5 is equal to 125. So that means that 5 cubed is equal to 125. So, this is this. It gets easier as we go on. Next one. Just scroll a little bit. Same thing here. You write equals x. This is going to be another switch. So you write b of x is equal to 81 to the power of 3. Now, this looks like a ton of work. So I'm going to give you the very classic tip here. Rewrite to have both sides use the same base. I've actually did that in the second problem. And the second problem was a bit more obvious because we have a relatively simple right side minus the reciprocal. But here it's not so obvious. Here you have a cube root and you have an 81. So it's not super obvious that it's actually going to have a similar base. So here it's kind of good to kind of think about that. So what's going to happen? Well, cube root of 81 is the same as writing 81 to the power of 1/3. And you can also write 81 as 3 to the power of 4. So in the end, the right-hand side can actually be rewritten as 3 to the power of 4/3. So you can write 3 to the x has to be equal to 3 to the power of 4/3. And similar to what you did in the second problem, line them up. These two things are equal. You get 4/5. There's a lot of guessing and checking that goes into it. On the calculator, obviously, like they do like some crazy estimating. It's actually quite fun to read into that, but we're not doing that. For the last one, is actually going to be the exact same setup as the previous problem. You still say that this is equal to x. You write it as 5 dx equals 243 to 125. Now I can go ahead and do some little scratch work on the bottom. 4th root of 125 is the same as 125 to the power of 1/4. 125 is 5 cubed, which we just saw in the first problem. So this is going to be 5 to the power of 3/4. So in other words, we have 5 dx is equal to, 5 dx is equal to 5 to the power of 3/4. And again, It's just arithmetic, I promise. It's just arithmetic. So the important thing here is this stuff here. So you have to rewrite it as 5 to the power or something. 125 is the easier one. That's just 5 cubed, right? And then the fourth root is going to be always a quarter, which is 1 over whatever the number is. And so then you just multiply the exponents, 3 times the quarter. A lot of tiny arithmetic. I promise when you do this on your own, after like an hour. Yeah, so it gets it. But yeah, I mean, like, obviously, like, some people just have done this enough where they'll see it and they know it. But if you haven't, then just keep it back. That's why I wrote that about it. Like, that's what I've done when I write stuff. I don't see it immediately. I just start writing down powers. That's what I get to. Now, you shouldn't immediately recognize it. Okay, a few more. So same exact thing. We're going to do these in the classical way, where you set this equal to x, and you solve. And I want to emphasize that there's nothing here, so assume the base is 10. So in other words, you have 10 to the x is equal to 100. Well, that's pretty easy. 10 times 10 is 100. So in other words, you have 10 squared is equal to 100. So this has to be 2. Not too bad. For the second one, same exact thing. You write this equal to x, switch these guys, and you get 4 to the x is equal to 2. Well, there's 2 ways you can do this. You can think of it as a square root if you want, right? If you take a square root of 4, you get 2. However, there's another way you can do this. Another way you can do this is notice 4 is equal to 2 squared. So you can actually write this as 2 squared to the x is equal to 2. This gets mapped into 2 to the 2x is equal to 2. And now it's about matching exponents. Well, if the 2 is by itself, assume there's a 1. Okay. These must be equal. So these must be equal, so 2 to the x is equal to 1. In other words, x is equal to 1. And this should make sense. This should make sense because 1/2, an exponent of 1/2 means you're taking a square root. So square root of 4 is 2. You should be able to recover that. You shouldn't see it necessarily immediately, but that's just a good check to have in your head. For the third one, same thing. We're going to have no base. So again, you assume it's 10. So you have 10 to the x is equal to 0.001. Now, I don't know if any of y'all have done scientific notation in a while, so it's okay to have it. It's all good. You can write 0.001 as the following. Is equal to 10 negative. Right? And the idea here is I can kind of show it. It's like you're taking the exponents. You're taking the exponents and going back. So 1, 2. It's a little bit weird. You have to kind of and so from there, you kind of have this situation where you can write 10 to the x is equal to 10 to the negative 3. Match them about this, which is what I meant to write, is you can think of this as 1 over 10 cubed. It's the same thing as 1 over 10. Which is equal to 10. It's going to be, what's this? It's the same thing as writing 1 divided by 1,000, which if you do that computation, gives you a number. And the last one is going to be more of the same. We write this is equal to x, switch, you get 40x is equal to -2. And this is actually a trick question. This is actually a trick question, which is going to lead us into a very crucial property of lots. What you should notice here is that this left side is always positive. And this side is negative. So in other words, these two pieces of information imply that this is impossible. And so the answer is does not exist. And crucially, the big hint for all this is that you can never plug in, or actually I'll say this as opposite. Negative or 0 into log. The idea here is that the range is only positive numbers. And you can also kind of think about this with the graph, which is essentially what we're trying to lead into here. We're just trying to kind of give you this nice and slow lead up. You show you the algebra, so you get to evaluate logs at the very basic level, and then you toss the graph.